Hello everyone, welcome back to this channel. So let's start a new course, Intermediate Machine Learning. We have completed Intro to Machine Learning. Now the next step is Intermediate Machine Learning. Okay, first as usual I will read the tutorial, then we will do the exercise. See here. Review what you need for this course. Okay, this is the introduction. If you have some background in machine learning and you would like to learn how to quickly improve the quality of your models, then you are in the right place. What are the things we are going to learn? How to tackle data which are found in real world dataset like missing values, categorical values, then how to design pipelines to improve your machine learning code, how to use advanced techniques for model validation like cross validation. Don't worry, we are going to learn these things. Okay, and how to build XGBoost, which is one of the robust model in machine learning, and how to avoid common mistakes. Okay. Now, along the way, you will apply your knowledge by completing a hands-on exercise, and this use data from housing prices competition. Okay, so where you will use 79 different explanatory variables such as the roof, number of bedroom, number of bathroom to predict the home prices. You will measure your progress by submitting predictions to this competition. Okay, now prerequisite. You are ready for this course if you have built a machine learning model before, you are familiar with this topic. Intro to machine learning which we completed before. There we studied model validation, underfitting, overfitting and random forest. If you are completely new, then you have to study this one. This one I have already explained. If you have not seen that video, then watch that first. Okay, now let's do the first exercise. Okay, first you have to set up. So for that you just have to run this. Okay, import OS. If not, this is all for setting up this exercise. Now you will work with the data from housing prices competition for Kaggle and users to predict home prices in using 79 explanatory variables they have already said. So run the next code without changes to load the training data and validation features. See, pandas imported. Let me first run and train test split. This is the CSV file which is converted to data frame, and this is the output, that is you have to predict the price. These are the features which you are going to use as input, and you are making the trend test split. Okay, all these things we have understood before. Now use the next cell to print the first several rows. So first 5 rows, these are the inputs and you have to predict the price. Okay, this is your data set. Now the next code cell defines 5 different random forest model. Run this code cell without changes. Okay, so don't make any changes. They are using random forest. You know what is a random forest? Random forest means when you are taking suggestions from many decision trees, that is known as random forest. So random forest regressor where the estimator is 50 random state and 50, 100, 200, 100 and different kinds of parameters they have used and created 5 models. Okay. Now which one is the best? Here as they have changed the parameter, they want to check which one is giving you a very good performance. So you have to select the best model. So to select the best model, we can define a function called score model. This function returns the mean absolute error. How to find which one is best? The model which provide minimum error. Okay, so you have to calculate the error, and the model which is giving you the least error is the mean absolute error. Okay, now run the cell code without changes. So from sklearn.matrix import mean absolute error def score model. So xtrain, xvalid, ytrain, yvalid, model.fit, model.predict and return mean absolute error. For I in range 0 to length of models, MA equal to score model. So you are creating a for loop, and you know range function generates 0, 1, 2, 3, 4 up to the lane of models minus 1. Why minus 1? Because the last one is excluded. It's starting from 0. Okay, now you are calculating the mean absolute error. How you are calculating mean absolute error? By calling this function, that is score model. So here you are passing the model. So first model 1, model 2, model 3. See, this is the arguments. So you are passing it here and you are splitting them. After that you are training the model, then you are making the prediction from the model, and you are returning the mean absolute error. So once you return the mean absolute error, that is stored here and that is printed. So see, the first one, first mean absolute error for the model 1, second for model 2, mean absolute error for model 3, model 4, model 5. Okay, now you have to evaluate how you have to find which one has the minimum. So use the above result to fill in the line below. Okay, which model is the best model? Your answer should be one of model 1, model 2, model 3, model 4, model 5. Now anyone can say from here which has the least error. Which one has the least error? 24, 23, 23, 23. So we can see model 3, right? Okay, so you just have to write model 3. That is what they are asking for. So sorry, model 3. Okay, now this one is also in small only. Now generate test predictions. Great, you know how to evaluate what makes an accurate model. Now it's time to go through the modeling process and make predictions. Okay, in the line below, create a random forest model with the variable name my model. Create a random forest model with the variable name my model. Okay, so this is your model name, which is the best model. So you just have to write best model. Okay, simple thing. Now run the next code cell without changes. This code feeds the model to the training and validation data and then generates test prediction that are saved to a CSV file. See, now your model is my model. That means you are taking the third model. See, random forest regressor, n estimator is 100, criteria is absolute error, random state 0. These are all known as parameters. You can give different kind of parameters to check which model is performing well. So to know these things, you have to study decision tree and random forest in details, which we are going to cover later. Okay. And now as we have selected the best model, so we can just use that model to fit. Okay, fit method, you know, I have explained this many times before, and these are the training input, training output. Okay, so model is trained here. Once the model is trained, now you are using that to predict the value from the test. This is the test column. These are the rows you have kept for testing. These are not used for training. Okay, so once you predict, you are just saving it into preds underscore test. Okay, now you are saving the predictions and you are creating a data frame. This also we understand in our first class of intro to machine learning, how to convert a CSV to data frame, how to create a data frame. So here you are creating a data frame. Okay, you are creating a table where this is the input and this is the output. ID is the input and sell price is the output, and you are converting it into two CSV file, and this is the name of your CSV file. Okay, submission.csv is the new name of the CSV file, and you are converting it by it to underscore CSV. So you are converting it from data frame, because here you have created the data frame. So you are converting from data frame to CSV file so that you can submit. Okay, so now you can submit the result, join competition. You can do anything. Anyway, in our next class, we will understand how to work with missing values, because often you have to come across the missing values in your real data set. Okay, so meet in our next class. Till then, bye. Happy learning. Hello everyone, welcome back to this channel. So let's continue intermediate machine learning. In our last class, we did this introduction lesson. Now we are going to understand about missing values. First we will read, then we will do the exercise. Whenever you work with any real data sets, you may have to deal missing values. Okay. Now in this tutorial, you will learn three approaches to dealing with missing values. Then you will compare the effectiveness of these approaches on real world data set. Okay. So introduction. There are many ways data can end up with missing values. For example, a two-bedroom house won't include a value of for the size of a third bedroom, right? A survey respondent may choose not to share his income. So maybe due to many reasons there are some missing values in your data set. But your algorithm will not work within missing values. So you have to clean your data. Either you have to remove them, delete them, or you have to replace them with some other values. Okay, you cannot provide any missing values to your algorithm. It will not give you a good result. Okay, that is fine. Most machine learning libraries give an error if you try to build a model using data with missing values. Okay, so that also may happen. So you have to choose any strategy. Three approaches. First one is a simple option, drop columns with missing values. Okay, there is a missing value, drop the column. Okay, so what will happen? You have missing values in bed column, so it is deleted. Now you are with only single column. This is not a good approach, you also can say this. Unless most values in the dropped columns are missing, this model loses access to a lot of information, right? You have a data set with 10,000 rows and one value in a particular important column may be missing. So what will happen? The complete column will be deleted. That is not expected at all. But this is an approach. Okay, so we will find a better approach. That is imputation. Imputation fills the missing value with some number. For instance, we can fill in the mean value along each column. So here you are not deleting this, but you are replacing this with mean value. Okay, in some scenario you may have to replace with median value, or you may replace with mode value. Okay, but let's think that you are replacing it with mean value. So this is not right, this may not be correct. Okay, the value may be extremely high, may be extremely low, but better than this approach, right? You are not deleting, at least you are replacing this, so you are keeping this column. Okay, so it will lead you more accurate models. Now what is the third approach? An extension to imputation. Imputation is a standard approach. Okay, works well, fine. However, imputed values may be systematically above or below their actual values which were not collected in the dataset, or rows with missing values may be unique in some other way. That also may happen, that maybe these values were unique. Okay, so in that case your model would make better predictions by considering which values were originally missing. Okay, so here see, you are replacing the values. Now your model doesn't know that there was any missing value, it has all the values. But what if you tell them that earlier it was missing, now I have replaced it with this one. So you are giving an extra information, you are adding one more column by stating that this value was missing before, that is why this is true, and these values were not missing. Okay, so in second approach you are just replacing the values. In third approach you are also giving an extra information stating that this value was missing before. Okay, now in this approach we impute the missing values, and additionally for each column with missing entries in the original data set we add a new column that shows that this was missing before. Okay, now example. In this example we will work with Melbourne data set. Okay, so our model will find number of rooms and size, and then it will predict the price. Okay, the output will be price. So let's say see the hidden code. Pandas imported, same, price is the output and all others are input. You have done trend test split. Okay, now you are defining a new function, that is score dataset. This will compare different approaches to dealing with missing values. Okay, so you are just calculating what is the accuracy by this function. So random forest, you know, collection of decision trees. Mean absolute error, this is for predicting the accuracy. Okay, now this is a data set, you are passing all the values, you are fitting, predicting, and you are calculating the error. This will calculate you the error so that you can understand that how these approaches are actually working. Okay, now first approach. See, since we are working with both training and validation dataset, we are careful to drop the same columns in both data frames. Exactly. First approach is you are deleting the column. So you have splitted the data, training dataset, validation dataset. So if you drop, you have to drop from both of the data frames. Okay. Now columns with missing values. Column for column in extend.columns if it is null or any. If you find that there is a missing value, just keep it in columns with missing. Okay. Now what you are doing? You are just dropping. Drop function will drop these columns with missing. So those columns having missing values will be dropped. Okay. And x is equal to 1 means you have to say this. Now you are printing the mean absolute error. This is the error. Okay. Now let's see the approach 2. Approach 2 is you are using simple imputer. This will help you to replace this with mean value. Okay. So my imputer equal to simple imputer. Now imputed extend equal to pd dot data frame. You are doing the fitting and transform together for training data frame extend, and for validation you will not fit but you will transform. Okay. So this will replace your missing values. Okay. Now when you have removed the column names, you have to put them back. So you are renaming the column names. Although it's simple, filling in mean value generally performs well, while statisticians have performed with more complex ways to determine imputed values, such as regression imputation for complex strategies typically give no additional benefit once you plug the results into machine learning models. See, there are many types of things: mean value, median value, mode value, by which you can replace the values, or you can also learn some algorithms to find which one will be better for that missing values. Okay, there are many ways by which you can change your missing values. Okay, so now see the MAE value from the first approach, from the second approach. So you can say that approach 2 is better. This one may not be the best, but better than first one. Okay, so don't just delete but replace. Okay, now see this third approach. Okay, first you are creating copies, no problem. Now you are creating a new column was missing, so that you can tell the algorithm that it was previously missing. Okay, now you are calling simple imputer so that you can replace the missing value with mean value. Okay, now here we are doing fit transform on training data set, transform on validation data set. Okay, now imputation removed column names, so you have to put the column names back. Okay, now you are calculating the MA. See, it was 1781.66. Here maybe ORS. Exactly, it has performed slightly ORS. So why did imputation perform better than dropping the columns? The training data has 10,864 rows, 12 columns, where 3 columns contain missing data. Okay, so for each column, less than half of the entries are missing. Thus, dropping the columns removes a lot of useful information. Exactly, so it makes sense that imputation would perform better because you have removed so much. This is very logical. Okay, so you just check this one, you can understand that why it is performing better. Now, as is common, imputing yielded better result relative to approach 1. Okay, now let's do the exercise. So first we have to make the setup. So let me run this, and now same coding, just importing, creating output, input, doing the train test slate. Now use this one. Okay, Melbourne housing prices data set, all these things are input and you have to find the price. Okay, now you have got the extent. Now you are checking the training shape and how many values are missing. Now how many rows are in the training data? Number of rows 1168, number of columns 36, number of columns with missing values 1 2 3. Okay, so write it 3, and total missing values, so you have to add them: 212 plus 6, 218, 218 plus 58. Okay, add them, those values are missing. Okay, so what is your first approach? Deleting all these 3 columns. Second approach, replacing them with mean values. Third approach is also telling that these values were missing before. Okay, now part B. Okay, so random forest, you know, mean absolute error, you are calculating the score, this will give you the accuracy. Now drop columns with missing values. Okay, so fill in the line below, get the names of the column with missing values. Okay, let me copy this. So how to get this one? Columns with missing values, right? So just copy, you try to write it. Okay, fine. Now what is reduced extend, what is reduced x valid? Okay, we run this. Correct. Okay, so run the next code cell without changes to obtain the MAE for this approach. Score dataset is not defined. Why? Okay, we forgot to run this one. So you have to run this, then you can check what is the score. This will not be good. Okay, now step 3, imputation. So use the next code cell to impute the missing values, right? So here also you have to do the same thing. You just have to use simple imputer. Okay, so we will again copy. This is you have to use. So just copy the whole thing. See, um, delete this one. First you have to create an object of simple imputer function. Now you are using imputed extend. So you are doing this on training data, you are doing this on validation data. Okay, now you have to rename this column because the columns are deleted. So now fill in the lines below. Imputation removed column names, put them back. Sorry, it has been copied twice. Sorry. Okay, so now let me run. Okay, now print this one 18062. Yeah, does anything surprise you about the results? What do you think, one approach better performed than the other? Why do you think that this one approach performed better than the other? So, given that there are so few missing values in the data set, we would expect imputation to perform better than dropping columns. However, we see that no, it is exactly opposite. So, dropping columns was a better choice. But why is that so? That may be due to some noise or maybe some other explanation. This may be instead of filling the mean value, it makes more sense to set every missing value to a value 0 or to fill in the most frequently encountered value, okay, or to use some other method. For instance, consider garage year built column. It's likely that in some cases missing value means the house doesn't have a garage, but what we are doing here, we are replacing it with mean value. So does it make more sense to fill in the median value along each column in this case, or median value? So could we get better results by filling the minimum value along each column? It's not quite clear which one is the best. That's what I have stated you, that there are many approaches. So you have to find out which one is the doing the best result. Okay. Now step 4. In this final step, you will use any approach of your choosing to deal with missing values. Okay, your choice, they have stated. Once you have processed the training and validation features, you will train and evaluate a random forest model. Then you will pre-process the test data before generating predictions. Okay. Now use the next code cell to pre-process the training and validation dataset. See, here they have stated use as per your choice. So what we can do, uh, let me copy this first. Then we will edit. Okay, first we paste this one. Okay. So here they are saying that give a strategy parameter. I told you that you can use any value, median or mode. So if we use median, okay. So now let me copy this final extend. So okay, final x valid. This is fine. Okay, so in here you are doing fit transform for training data, you are doing transform for validation data. Now your column is deleted, so you have to write the column to put them back. So you have to copy this also, right? So after imputation the column names are deleted. So what you have to do, sorry, final string, this one will be validation data set. Okay, fine. Now run the next code cell to train and evaluate random forest model. Okay, note that we don't use the function above because we will soon use the train model to generate test predictions. Okay, no problem. Random forest model fitted predicting your mean values. Now use the next code cell to pre-process your test data. Make sure that you use a method that agrees with how you process the training and validation data, and set the process test features to final x set. Okay, so in order for this step to be marked correct, you need to ensure the processed test frame data frame has no missing values and it has the same number of rows as x test. Okay, no problem. So final x test equal to, what you have to do, you have to pre-process the data, right? So for that you can write pd dot, let me write this one, data frame. Here the name is what, my imputer. So my underscore imputer and you have to transform. Here you are not going to do fit, right? Because you are doing it on test data set. So X test. Perfect. Now you have to predict. So just write model dot predict, and here you have to give this name final X test. Okay. So you have processed the test data. You are predicting the test data. Um, okay. Now run the next code cell to save your results to a CSV file. Okay, so save your results and submit your results. Okay, so we have completed this course. Now you take any real world data set and try to apply all these strategies. Okay, so meet in our next video. Till then, bye. Happy learning. Hello everyone, welcome back to this channel. Let's continue intermediate machine learning. As of now, we have completed introduction and missing values. Today we are going to understand categorical variables. Categorical variables means non-numeric. So, in this tutorial, we will learn what a categorical variable is along with three approaches for handling this type of data. Categorical variables means different kinds of category. A numerical variable means number. If you don't know, I have a blog there I have written about types of data. You can just give it a single read. This is a categorical variable, whether roti or rice. Numerical means how many rotis you are asking for or how much rice you are asking for, that is numerical variables. Okay, and numerical variables can be divided into two types: continuous, discrete. Categorical variables can be divided into two types: nominal, ordinal. Nominal means when there is no particular order, but ordinal means when you have some order. It's like you have high school diploma or bachelor's degree or master's degree. These are distinct ordered categories. Okay, you just can give it a single read. Anyway, this topic is about categorical variables. So, introduction. A categorical variable takes only a limited number of values. Consider a survey that asks how often you eat breakfast and provide four options: never, rarely, most days, every day. So, you have to choose any one among all these options. Okay. So, these are limited. It's not like numerical, you don't have infinite values. So, in this case, the data is categorical. If people responded to a survey what types of car, whether it is Honda, Toyota, Ford, there are different categories. So these variables are called categorical variables. Okay. Now, the problem is that if you try to plug these variables into machine learning models without pre-processing, your model will not work. So first you have to pre-process them, because machine learning model doesn't understand string. Okay, it only understands numerical values. So you have to convert these strings into numerical values. Now how? That is what we are going to learn today. Okay. So there are three approaches. First one is drop categorical variables. That is the simplest approach. We learned this category while handling missing data also. You just simply drop the variable. You think, okay, there is a categorical variable. Okay, remove that column. Okay, but that is not useful when you need that particular column, right? Next approach is ordinal encoding. Ordinal encoding assigns each unique value to a different integer. It's like, see, never represented as 0, rarely 1, most days 2, and every day 3. So you have given a order 0, 1, 2, 3, and every value is represented by different number. This is known as ordinal encoding. Okay. So whenever you again get most days, what will be the value? 2. Okay. So you are pre-processing your column which contained string before, which contained categorical values, now converted to numerical variables. Okay, now it is containing numerical values. Now you can give this column to your machine learning model. Okay, clear? Now there is an indisputable ranking to categories. Not all categorical variables have a clear ordering. That's what I have told you here also. Some values do not have any particular order. It's like roti and rice. You cannot give them any order. So they are under nominal categories. But when you are following an order, then you are actually using ordinal variables. Okay. Fine. For tree-based models, you can expect ordinal encoding to work well with ordinal variables. Now the next approach is one-hot encoding. One-hot encoding is going to be used most of the times. So it creates new columns indicating the presence or absence of each possible value in original data. Now see how it works. You have three types of color: red, yellow, green. Okay. Now in the first what you have to do? You have to create column names with unique values. Red 1 value, yellow second value, green 3. So red, yellow, green. Okay, so you have created 3 columns, the number of unique categories. Okay, fine. Now what you are doing? First, you are giving red as 1. So it is 1. Now yellow 0, green 0. So when machine learning gets the first row, it understands that the value is red. Okay, because this is 1. Then second one, see, this is 1. But in case of yellow, you have to make yellow as 1, all others as 0. In case of green, you have to make green as 1, all others as 0. Okay, what if there is one more category, let's say blue, then you have to create one more column. Let me show you. Then you have to create red, yellow, green and blue. So in case of red, you will give 1, all others 0. In case of yellow, yellow will be 1, all others will be 0. In case of green, so it will be 1, others will be 0. In case of blue, all will be 0 and it will be 1. Okay, simple thing. This one will be 1. Okay, next if it 1 comes yellow, then again 1, it will be 1, others will be 0, right? This is known as one-hot encoding. In the original dataset, color is a categorical variables with 3 different categories. So one-hot encoding contains one column for each possible value and one row for each row in the original dataset. Exactly. Whenever the original value was red, we put 1 in the red column. When it was yellow, we put 1 in the yellow column. That's what I have said. Now in contrast to ordinal encoding, one-hot encoding does not assume an ordering of these categories. You can understand that, you can understand that there is no particular order, right? But in case of ordinal, you have an order, right? So one hot encoding does not assume an ordering of the categories. So you can expect this approach to work if there is no clear ordering. Okay, and this is the intrinsic ranking of nominal variables. Okay, one hot encoding generally does not perform well if the categorical variables takes on a large number of values. That you can understand. Let's think that there are so many values: red, yellow, green, blue, violet, and many others. Then what will happen? You have to create columns for each of them. So how many columns will be generated? So many. So it never works very well with large number of categories. Okay. You generally won't use it for variables more than 15 different values. Now, the previous tutorial we used Melbourne housing price dataset, so we are going to work with this only. See, same thing, I am not going to repeat. Price you have to calculate, Melbourne housing prices dataset, and missing value columns are dropped. Okay, and now this is the thing right now we have. Okay, now we obtain a list of all the categorical variables in the training data. Okay, so we can check this by using dtype. You know, dtype data type, it will help you to check which types of data is existing in the column. So if you write extend.dtypes equal to object, then keep it in object underscore column. So it will give you a list of all the categorical variables. Okay, if it is object, keep it in object underscore columns. So now you can print the categorical variables: type, method, region name. These are categorical variables. So you have to first pre-process these categorical variables before you give it to machine learning algorithms. Okay. Now the score dataset function, it compares 3 approaches to dealing with categorical variables. It will calculate MAE, the same we used before also. See, random forest, fitting, predicting, error calculation. Okay. Now what is the first approach? Score from approach 1, we drop the object columns with select dtypes method. Okay, so this method will be used to select the to drop the object columns. Now see, extend dot select underscore dtypes exclude object. Drop x valid, select underscore dtypes exclude object. You are doing this for training, you are doing this for validation. Okay, now you are calling this function. So you are passing extend, drop x valid and y train y valid, and it will give you a score. Okay, so this is the score. First one. Second approach, ordinal encoding. Here you have to import ordinal encoder. Now you are creating copies so that it doesn't get lost. Okay, now first you have to create an object. As usual, you have to create an object. Using that object, you will call first fit transform, then fit transform for training objects, and then transform for validation. Okay, you are not fitting for validation. Okay, extend object columns when these columns are holding string values, categorical values, all these 3 columns. Okay, because you have kept them in object underscore columns, so you are here passing those columns and you are transforming them. Okay, now you are checking the score. See, earlier it was 17, now it is 16. So we randomly assign each unique value to a different integer. This is a common approach that is simpler than providing custom labels. However, we can expect an additional boost if we provide better informed labels. Let's see, one hot encoding. For using one hot encoder, you have to import one hot encoder. This one. Okay, you have to create an object first, then you can apply one hot encoding. There are a number of parameters that can be used. Okay, handle unknown, this is a parameter. This is to avoid errors when the validation data contains classes that are not represented in the training data. Let's say in validation data you may get something new, okay, that is not in the training data. So what it will show you? It will show you an error. It will tell you that I have not seen this in training, during training, so how can I give you an output? So to handle this kind of error, simply error handling, or I can say exception handling, you are using handle underscore unknown equal to ignore. Okay, now setting sparse equal to false means that sometimes it returns sparse matrix. Sparse matrix means it has too many zeros in that particular matrix. So to handle those sparse matrix, you have to write sparse equal to false. Okay, so that you can ensure that encoded columns are returned as a numpy array. If you don't give this, sometimes it shows an error because it faces problem with the sparse matrix. Okay, now to use encoder, we supply only the categorical columns and we want to be one hot encoded. Fine, for instance, to encode this training data, object columns, list of columns holding object data, and so X10 contains all of the categorical data in the training set. Okay, so see, as usual, you have to create an object. They are giving two parameters that handle unknown values and handle sparse matrix. Now you are using this feed transform and transform on validation. Okay, so you have applied one hot encoding on categorical columns. Now one hot encoding removed index, so you have to put the index back. So extend dot index equals to this new dot index. Okay, so index are regenerated. Now you have to remove categorical columns and you will replace this with one hot encoding. So you are doing extend dot drop object columns. Remove all those values, all those columns where it is containing a string, right? Same for X validation. You have to do this for all of them. Now what we have to do? We have to add this applied one hot encoded columns. Okay. So for that pt.concat, this is where you have stored the one hot applied encoded columns, and x is equal to 1 means you will answer in the comment section. And same it is for validation. Okay. Concat method will help you to concatenate. Now ensure all the columns have string data type. So for that you are using as type. You know about as type function. It helps you to convert the data type of any particular column. So you are converting it into string. Okay. If it is not in string, it will be converted. You are just ensuring. Okay. Now you are printing what is the value. So you are calling score data set. It will be trained. It will be predicted. It will calculate the accuracy. Okay. Now, which one is the best? In this case, dropping the categorical column performed worst, since it had highest MA score. As for the other two, since the returned MA scores are so close, it doesn't appear to be any meaningful benefit. So in general, one hot encoding will typically perform best and dropping the categorical columns typically performs worse. Okay, it in general, but machine learning is all about trial and error. Okay, so it is not like that it will always give you the best result. It depends on the types of data and types of algorithm and what is your purpose. Okay, so the world is filled with categorical data. You have to be very much effective. So let's do the exercise now. First you have to do the setup. Okay, now you are will work with this data set. So let's run this. Same, you are importing pandas, you are importing train test split, and you are removing the columns with missing values. Price you have to, the setup is complete, not yet. Price you have to calculate. To keep things simple, we will drop columns with missing values, break of validation from training data. So all these things are as usual, and here you can see the training data set. Okay, just wait for the setup is complete, and this is also done. So let me run this one. Okay, see, you have to calculate the price. So you can see so many categorical columns. Let's see. Okay, notice that dataset contains both. You will need to encode categorical data before training a model. To compare different models, same score dataset. We will just run this. Same thing, you're just training, you are just predicting, you are calculating error. Now, drop columns with categorical data. You will get started with most straightforward approach. Use the code cell below to pre-process the data in extend and X validation to remove columns with categorical data. The first approach. See, I will copy, but I will suggest you to write it by yourself. Okay, where is that? This one. Okay, you have to drop this. So drop extend, drop X valid. Let me copy both of them. Okay, run the next code cell to get MAE. See what is the error. 17. So before jumping into ordinal encoding, we will investigate the dataset. We will look into condition 2 column. Okay, let's see. This code cell prints the unique entries in both the training and the validation dataset. Unique values in condition 2 column in training data, norm, POSA, FEDR, POSN, artery, all these have some meanings, norm. Okay, so you know what is unique? It will give you the unique categories. Okay, training column, the column names, and in the validation column, the column names are different. This column is not present in training dataset. This column is not present in training dataset. Okay, so there may be a problem. Let's see. Ordinal encoding. If you now write code to feed an ordinal encoder to the training data and then use it to transform both the data, then you will get an error. Why is that so? You can understand that there are problems with column names. Okay, so what happened? You are training these columns, you are giving them a number, unique number. But in case of validation, this one didn't get any number during training. Okay, so it will throw an error. It will ask who am I and what is my number, and there will be no answer. So there will be a problem and it will give you an error. Let's read this. Fitting an ordinal encoder to a column in the training data creates a corresponding integer valued label for each unique value that appears in the training data. You will get a value for this one, for this one, for this one, for all of them. But this one is not present here, so it is not getting any value, right? So in that case, the validation data contains value that don't also appear in the training data, then it will throw an error because you have not assigned any value. Okay. Now, there is a common problem, you will face this problem. For instance, you can write a custom ordinal encoder to deal with new categories. But it is better that you drop the problematic columns and you keep the good level columns. Okay, first see. Here, what you are doing, you are first taking the categorical columns that we have done before also. You are just selecting all those columns where the data type is object and you are keeping them in object columns. Okay, so these columns are categorical columns. Now you have to separate good columns, bad columns. So how? First one, you are creating a for loop on these particular columns, on those categorical columns, and you are checking that whether the validation dataset is a subset of training dataset. That means all those columns which are present in the validation dataset are also present in the training dataset. Okay, so you are checking whether this set is also a subset of this one. Okay, this is a set data type in Python. I hope you know. Each subset is used to check whether all these values in X validation is also present in all the in the training columns. Okay, in the training data set. Okay, so once you get them, you are storing them into good level columns. Okay, so you have all the columns, you have got the good level columns. Now if you subtract them, then what will be remained? The bad level column, simply. So you are creating a set of this one, you are creating a set of this one, you are just subtracting and you are keeping the result into a list. Okay, so these are the good level columns, these are the bad level columns. Perfect. Now use the next code cell to ordinal encode the data in extend and xvalid. Set the preprocessed data frames into okay. So first drop categorical columns that will not be encoded. So you are dropping the extend dot drop bad level columns you have just selected. So you are just dropping them. Okay, access equal to 1, you column wise you are dropping. Now you have to apply ordinal encoder. Again I am going to copy. See, first you have to create an object. You have to do fit transform on training and transform on validation. Simple concept. Okay, send this. See, found unknown categories because these categories were not present in column 9 during transform. Okay, because here we are applying this ordinal encoding on the object columns, that is this one. So what you have to do? We have to do this on good level columns, right? So just copy this and paste it here. Good level columns, good level columns. Okay, now let's run this. Okay, run the next code cell to find the MAE. 1700. So far you have tried two approaches to dealing with categorical variables, and you have seen that encoding categorical data yields better results than removing columns. Now we are going to use one hot encoding. Okay, first get the number of unique entries in each column. Okay, so we are taking lambda anonymous function, we are taking the training data set, we are calculating how many unique columns on categorical variables, then we are creating a list of that. Then we are grouping the columns with respective unique numbers and creating a dictionary. After that we are just sorting item wise, okay, ascending order. Fine. Now, investigating cardinality. The output above shows for each column with categorical data the number of unique values in the column. For instance, the street column in the training data has two unique values, GRV1 and pave, corresponding to a gravel road and paved road. Okay, for street column you have two unique entries. Now we refer to the number of unique entries of a categorical variable as the cardinality of the categorical variable. So street column has 2 cardinality. Cell type column has 9 cardinality. Okay, the types, total number of types is the cardinality. Now use the output above to answer the questions below. Okay, so fill in the line below how many categorical variables are in the training data have cardinality greater than 10. So greater than 10. 25, 16, 15. So exterior first, exterior second and neighborhood. 3. Fill in the line below how many columns are needed to one hot encode the neighborhood variable in the training dataset. 25. I told you while doing the red, yellow, green. So if you have red, yellow, green, there will be 3 columns. If you have red, yellow, green, blue, you will have 4 columns. Okay. So number of unique types of values. So you have to use 25 categorical columns. Fine. Now for large dataset with many rows, one hot encoding can greatly expand that we have discussed. For this reason, we typically will only one hot encode columns with relatively low cardinality. The high cardinality columns can be either dropped or you use ordinal encoding. Okay, so first you will check that unique types. Now if you see that these are huge like exterior second, neighborhood, exterior first, so you may avoid them for one hot encoding. You can do the ordinal encoding for them. Okay, because for one hot encoding it will be huge, the number of columns will be so many. Okay, that will be a problem. Now for this reason, we typically do this. Okay. Now then high cardinality columns can be either dropped or we use ordinal encoding. As an example, consider a data set with 10,000 rows and containing one categorical column with 100 unique entries. Okay. So if the column is replaced with the corresponding one hot encoding, how many entries are added to the data set? If this column is replaced with the corresponding one hot encoding, one categorical column has 100 unique entries. For 10,000 rows, if there is 100 unique entries, then it will be 10,000 into 100. Okay. Now, how many entries are added to the data set by replacing the column with ordinal encoding? Nothing, because for ordinal encoding, you are not adding any extra column. Okay. Next, you will experiment with one hot encoding, but instead of encoding all the categorical variables, you will create a one hot encoding for columns with cardinality less than 10. Okay. So, run the next code cell below to set low cardinality columns to a Python list containing the columns that will be one hot encoded. Okay. So, high cardinality columns will be dropped from the dataset. Okay, so what you are doing here, you are separating them. You are first calculating what is the cardinality. That means how many unique values each column has. Okay, now if it has more than 10 columns, then you will simply remove them. If it has less than 10 columns, then you will do the ordinal encoding. Okay, that is the concept. So how we are doing? First, we are calculating the low cardinality columns for only those columns which has number of unique values less than 10. Okay, you are taking all those columns. And what are the high cardinality columns? You can just simply subtract. So subtract from all the categorical columns minus the low cardinality columns. So it will be kept in high cardinality columns. Okay. So see uh, these three, because these are greater than 10. Okay. Now if you want to take up to 15, so you can write less than 16. Then there will be two columns, right? Exterior second and neighborhood. Clear? Now you are applying one hot encoding. So you have to process extend x valid and keep it in there. Okay. So use as many lines of code as you need. Okay. What you have to do? Full list of categorical columns that can be found in Python list object columns. You should only one hot encode the categorical columns and all other columns should be dropped from the dataset. Okay, so let me first copy, then we will do the edit. This is ordinal encoding and we will do this for this one. So let me take the whole thing, then I will edit. Just copy and paste. See, this is fine. Ordinary hot encoder, you are just creating an object. Now you are transforming not only object columns, but you are doing this on low cardinality columns. So you have to copy this and you have to paste it here, right? For this also. Okay, now it has removed index, so you have to put the index back. You have to remove the categorical columns. You are adding one hot encoded columns, two numerical features, and you are ensuring all of them has. Okay, I think it is fine. Let me run this. MA from approach 3 incorrect. Wage extend should have 155 columns. Okay, sorry, here I have made it 16 for you, so that is why. So I have to do this 10. Now let me run this. Let me run this again. Now okay. Now run the next code cell to see the MAE. Generate text prediction. See, this is the error now, and submit your results. Okay. Okay, so we have done this one, categorical variables. In our next class, we will study how to use pipelines. Okay, bye, happy learning. Hello everyone, welcome back to this channel. So let's continue intermediate machine learning. As of now, we have completed these three lessons. First, introduction, then we have understood how to handle any missing values, then we have understood how to handle any categorical variables. Okay, today we are going to understand pipelines and then we will do the exercise. But before that, let me tell you a simple thing that we all know. Whenever we do any data science project, we have to follow some steps, right? First, you have to gather the data, then you have to clean the data or do different kinds of EDA like structuring, joining, merging. Then you have to do feature engineering, creating new columns or selecting only those columns which are necessary. After that, we do modeling, right? And then we do prediction, evaluation. Then we have to deploy. So there are different steps you have to follow while doing any project. So what pipeline does, it adds all the steps in a single place so that it behaves like a single step. That will help you in many things. Think that you have two different data sets. One is training data set, another is validation. You have testing data set. So whenever you are making any changes in training data set, you have to ensure that you are making the changes in validation data set. Let's say there are some missing values in training dataset. So whenever you are treating this missing value in training dataset, you have to make sure you are doing the same process in validation dataset, the same process in testing dataset. Okay, so you have to do so much manual work and there may be some inconsistency. Here it may have changed but not in the testing dataset. So there can be problems. Okay, so to solve this problem, there is a concept called pipelines. As the name suggests, pipelines means creating a pipe of all these steps together so that they behave like a single step. Okay, so it will help you to create automation, right? Once you put your data here, these steps will be automatically followed, right? Consistency will be there. Reusability, you can use it later also, right? And obviously efficiency will be increased. Okay, now let's read this, then things will be more clear. See, pipelines are a simple way to keep your data pre-processing and modeling code organized. Specifically, a pipeline bundles pre-processing and modeling steps so that you can use this whole bundle as if it were a single step. That's what I have said you. Many data scientists hack together models without pipelines, but pipelines have some important benefits. This is not necessary. Pipelines, it doesn't mean that if you don't create a pipelines, your project will not be executed. It's not like that. But it has some advantages. That's I have told you here, right? Let's see. Cleaner code, exactly. Accounting for data at each step of pre-processing can get messy. So with a pipeline, you don't have to worry about keep tracking or training data, validation data at each step. So it is a cleaner code. Fewer bugs, fewer opportunities to forget any pre-processing step. That's what I have told you here, that you are making some changes in training data set, but you have forgotten to do the changes in validation data set. So these types of problems will not occur. Okay. Okay, easier to productionize, so it can be hard to transition a model from a prototype to something deployable at scale, so we don't have to worry about that also. So these things will be taken care by pipelines. Now let's read the example. Melbourne housing dataset that we have seen before also, right? So you have training dataset, validation dataset, y train, y valid. Okay, this is how it looks: bedroom, bathroom, land size, longitude, year build, and you have to predict the price. Okay, we know this dataset. Now see the pre-processing steps. How a pipeline bundles together pre-processing and modeling steps. We use the column transformer class. It will help you to do this, to create this pipeline. So this imputes, the code below imputes the numerical data and missing values, applies one-hot encoding to categorical data. In our last class we understood how to handle categorical data, how to handle missing values, right? So this is a code. I will describe this code. First, they have imported column transformer. It will help you to create the pipeline. Okay, pipeline. The class is needed also. Simple imputer. Simple imputer will help you to pre-process the numerical data to impute the missing values in numerical data. Okay, that we know. And one hot encoder is used for encoding the categorical data. Right? That's also we know. So first you are pre-processing the numerical data. So you are calling the simple imputer class and you are giving a strategy. Strategy you can change. Okay. And here they are pre-processing the categorical data. So for categorical data, first they have imputed the missing values with most frequent. Most frequent means you are using actually the mode value, right? And one hot encoder, they are applying it so that it gets encoded. Okay. I hope you remember what is one hot encoder. Converting the categorical variables to numerical variables, right? Okay, now see how to bundle. So preprocessor equal to column transformer, transformers, numerical columns, categorical columns. Okay, so in the transformer you are sending the numerical values, then you are sending the categorical values. See here, whenever you are calling this numerical transformer, it will go here, numerical transformer. So it will impute all the missing values. Fine. Once done, you are calling the categorical variables. So you are calling categorical transformer function. So it will go here. So all these steps will be done. First, missing values are treated. Then one hot encoding applied. And now this is completed. Okay. So it is bundling the pre-processing step. This step and this step. Both of them steps are together. Okay. Now you have to define the model. So they have used random forest regressor. We know what is random forest? Collection of decision trees. Okay. So n estimator, number of estimator is 100, random state is 0. Now create and evaluate the pipeline. Finally, we use the pipeline class to define a pipeline that bundles the pre-processing and modeling steps. There are a few important things to notice. Let's say with the pipeline, we process the training data and fit the model in a single line of code. So in contrast, without a pipeline, we have to do imputation, we have to do one hot encoding, we have to model in separate steps, and this becomes really messy if you have to deal with both kinds of variables, right? Okay. So with the pipeline, we supply the unprocessed features in xvalid to the predict command. The pipeline automatically pre-processes the features before generating the predictions. Okay. So you are taking the validation data set, you are passing through this particular pre-processing. So automatically this pre-processing will be applied on your validation dataset as well. Okay. So without a pipeline, you have to remember to pre-process the validation data before making any predictions. Okay. Let me tell you once again. You have make some changes in your training dataset. Okay. You have imputed the missing values. You have done one hot encoding. Now, while predicting, you have a different dataset, that is the validation dataset, okay, or I can say that testing dataset. So in that scenario, you have to apply all those steps which you have applied in your training dataset to get your result. So you may forget that, you have to remember that. So instead of taking so much pressure, you just create a pipeline through which you have passed the training dataset. Through that pipeline you will pass the validation or testing dataset also. Okay, so you don't need to remember all the steps, and it will go through all the steps and will give you the predicted result. Clear? Okay, now see, mean absolute error, this is used to calculate the error. So here we are connecting them. See, pipeline steps are preprocessor and modeling. Preprocessor means you are calling this one. Okay, so in validation data set, you are calling this preprocessor. That means all the data points will go through numerical transformation, which is described here. Then we'll go through categorical transformation, which are described here. There may be many steps, okay, but it will go through all the steps. Once it is applied, then it will go to next step. What is the next step? Modeling. So it will call this one. So it will go through random forest regression. Okay, so you are making things simple so that you don't need to remember these things. You don't have to remember this one, you don't have to remember this one, then you have to remember the modeling. You may forget some steps. So this will help you to make these things organized. Okay, now you are fitting as you have done before also. You are predicting, you are calculating the error. Okay, so pipelines are valuable for cleaning up machine learning code, avoiding errors, and are useful for workflows with sophisticated data processing. Okay, but it doesn't mean that without pipeline you cannot do your project. You can, but you have to do some unnecessary manual work. There may be some errors, there may be some inconsistency, you may forget some steps. So to avoid all these things, try to use pipelines. That is the thing always used in any industry. Okay, now let's do the exercise. So this is the setup. And see, we are doing the trend test split. Remove rows with missing target from the predictors, break off the validation, categorical columns, numerical columns. Okay, fine. Let's run this. This is the data set we have. Okay. Okay, now let's see. Column transformer. So we have imported column transformer pipeline for creating the pipeline, simple imputer for treating the missing values in numerical columns, one hot encoder for handling the categorical values. Now random forest regressor, that is the modeling, mean absolute error for calculating the errors. Okay, now see, pre-processing for numerical data, simple imputer, strategy, categorical data, let's say simple imputer, strategy, and one hot encoder ignored. We have learned these things. Okay, thing that if I tell you changes this most frequent to mean value, suppose, okay, in any scenario. So if you don't use pipeline, what will be the problems? You have to make these changes for training dataset, for validation dataset, for testing dataset. So you have to make the changes 3 times and you may miss sometimes. So instead of doing that, if you just write it in a pipeline format, you will just change here and everything will be fine. Okay, so it is so much organized, you understand. Now you are bundling the pre-processing. Column transformer, so you are passing the numerical transformer, numerical columns, you are passing the categorical columns. Okay, you are defining the model, you are you are bundling the pre-processing steps and modeling. Okay, so these are the pre-processing steps and this is the modeling steps. Okay, you are fitting the model, you are predicting this model. Okay, so this yields for value of mean absolute error, whatever it is. So you are understanding how the complete thing is working together. Now, improve the performance. Now it's your turn. In the code cell below, define your own pre-processing steps and random forest model. Okay, so they are telling you to do the numerical transformer, categorical transformer, and column transformer. Same, right? For numerical transformer, I'll write this one: simple imputer, strategy, constant. This one. Okay, they are telling you that if you want, you can improve. But if you don't want, you just, I'm doing the copy paste. Okay, now for categorical transformer. Categorical transformer pipeline, you have to follow these steps. Imputer, one hot encoder. So instead of one hot encoder, you can use something else also. Or instead of most frequent, you can use constant also. Okay, so you can do some steps here. Okay, now preprocessor, you are connecting these two, and now you have to define the model. Here also, instead of using random forest, you can use something else. Okay, this is your job to experiment. So, okay, now let me run this. I have not made any such changes. Uh, why? Simple inputter is not defined. Okay, fine. Now run the cell code below without any changes. To pass this step, you need to have a defined pipeline in part A that achieves lower MAE than the code above. You are encouraged to take your time, try out many different approaches, and to see how you can get the MAE low. Okay, so this is your job. I will tell you to do some changes here, like change this strategy here. Instead of one hot encoder, you can use label encoder or anything else. Then use, instead of using random forest regressor, use XGBoost or linear regression or any method you think, depending on your data set, which one will be the best one. Okay, and try to make it lower. Okay, that you will be doing with, that you have to do by yourself. Okay, so that you have to do by yourself. Now here, let me run this. We don't need to make any changes. They have already given everything, fitting, predicting, calculating the error. Okay. Now generate text prediction. So pre-process of your test data and fit the model. Okay, they are telling you to pre-process the data. So here the name is my pipeline. So let me copy this. My pipeline dot predict. Predict will be done on testing dataset. Okay, perfect. Now let me run this. Okay, so run the next code cell below to save your result in CSV. You can submit in the competition. Okay, so we are done. You can submit the result. In our next class, we are going to understand about cross validation. If you want me to create more videos, please subscribe my channel. Meet in our next video. Till then, bye. Happy learning. Hello everyone, welcome back to this channel. Let's continue intermediate machine learning. As of now, we have understood how to handle missing values, how to handle categorical variables, how to create any pipelines for a project. Okay, now we are going to understand cross validation. This is about measuring the model performance. Okay, first we will read, then we will do the exercise. This is for better measures of model performance. Okay, so you will face choices about what variables to use, what types of model to use, whether linear, whether XGBoost, whether something else, what arguments to supply for, what are the parameters. So far you have made these choices in data driven way by measuring model quality with a validation dataset. You know validation dataset, training dataset and validation dataset. Let's say your data set has total 1000 row points. So you have to keep some portion for training, you have to keep some portion for testing or validating how your model is performing, right? So maybe generally we use 80-20%. So 800 rows will be used for training, 200 rows will be used for testing. Okay, now, there are some drawbacks. To see, imagine if you have a dataset of 5000 rows, you will typically keep 20% 1000 rows but leave some random chance in determining model scores. Maybe that one model is performing good on 1000 rows but not on another 1000 rows. Let's say, as I have told you, you have applied some model and you have trained your model. Now you are testing on these 200 data points. Now what is happening? This is giving you a good accuracy. So you will think that your model is performing well. But maybe on another 200 rows, not this one, but another 200 rows, this is not performing that well. Okay. So this is contradictory. 200 rows are giving you good performance, but another 200 rows may not give you a good performance. So better approach is you take a bigger validation data set, right? But what will be the problem with the bigger validation data set? There will be some problems. You have to take some data points from training to testing, then only you can make the validation data set bigger, right? But if you take away the data points from training data set, then on which you are going to do the training? Okay, so there is a problem. If you want to make the validation dataset bigger, you have to take the datasets from the training dataset. And if your datasets are less here, then your model will not be trained properly because you have fixed data points. Okay, now see how we can solve this problem. So at an extreme, you could imagine having one row of data in validation set. If you compare alternative models, which one makes the best prediction on a single data point, that will be a matter of luck. In general, the larger validation data set, the less randomness there is in measuring our model quality. That's what I have said to you, and the more reliable it will be. Unfortunately, we can get only a large validation set by removing rows from our training data. So smaller training data set means worse models, because you are not training, actually you have smaller data points to get trained. Okay, so how to solve this problem? The technique is known as cross-validation technique. We run our modeling process on different subsets of data to get multiple measures of model quality. Let's say we could begin the dividing the data into 5 pieces, 20%. So we will get 5 folds. Now first part is used for validation, other parts are used for training. Second part is used for validation, other parts are used for training. Okay, let me show you here. Our data set has 1000 data points. So what we are doing, instead of keeping 800 200, we are dividing it by 5 folds. Okay, so every fold has 200 data set, right? Now in your first iteration, you are taking these 200 data sets for validation, and these are used for training. Okay, in second iteration, you are used these 200 for validation, and all these, this one, this one, this one, and this one will be used for training, right? In our third set, these 200 are for validation. This is for training, 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 training. In the fourth, for validation. All others are will be used for training. So what is happening? In each iteration, you are using 800 rows for training, 200 rows for validation. But in every iteration, the validation rows, the validation data points are different. Okay. So here it was same, and training data set was also same, but we are changing here. The training data sets are also getting, sorry, training data points are also getting changed, and validation data points also. Okay, this technique is known as cross validation. Now let's read here. In experiment 1, we use the first fold as a validation data set, all others for training. Second experiment, we hold out the second fold and we are using others for training. So we repeat this process using every fold once as a holdout set. Putting this together, 100% of the data is used as holdout at some point, and we end up with a measure of model quality that is based on all of the rows in the data set, even if we don't use all rows simultaneously. Now, when should you use cross validation? Cross validation gives a more accurate measures of model quality, which is especially important if you are making a lot of modeling decisions. However, it can take longer to run because it estimates multiple models. Exactly, it is estimating different models, so it will be longer to run. Okay. Now, for given these trade-offs, when should you use this approach? For small data sets, when extra computational burden is not a big deal, you should run cross-validation. The computational burden is the problem. So when that is not the big deal, you can use second. For large data set, a single validation set is sufficient. Your code will run faster. You may have enough data that's there, little need to reuse some of it, hold out. If your data set is larger, what we said before, that we need a bigger validation data set. If it is already larger, then you don't need to do this, because this is taking your time, this is taking your memory. Okay, so for larger data sets, you may reject this. For smaller data sets, this may be a very good approach. Okay, but when we call it a large dataset and when we call it a small dataset, there's no simple threshold. It depends. If your model takes a couple minutes or less to run, it's probably worth switching to cross validation. Your decision, your call. Okay. Alternatively, you can run cross validation and see if the scores for each experiment seem close. If each experiment yields the same result, a single validation set is probably sufficient. Because every time if you are getting the same result, then you can say it's okay, it's fine, you don't need to do this. Okay, now we will work with some data. In previous tutorial we load in the input data sets. Let's see the Melbourne data set: rooms, distance, land size, building area, year built, and you have to use you have to predict the price. Exactly the same one. Random forest regressor, pipeline. In our last class we have studied about pipeline, and simple imputer to handle the missing values. Here see, pipeline has been created. First step is pre-processing. Pre-processing is done by simple imputer, missing values will be imputed. Okay. Second step, direct modeling. Here categorical variables, there is no categorical variables, so they have not bothered about that. In a pipeline, they have preprocessed and they have using model. Model is the random forest regressor, these are the parameters. Okay. Now see, we obtain the cross validation scores with this function cross underscore val underscore score. This is in scikit-learn function. So you are importing this one cross underscore val underscore score. Okay. Now you have to set the number of folds. This is not fixed that you have to divide it into 5. You can use 3, you can use 4. It depends on your data set. Okay. So here they have used 5. CV means that the folding, how many number of folds you want to do. This is the parameter, CV parameter. Okay. Now see, they have used -1 into cross val score. They are sending the pipeline. X is the training data point, Y the output, CV equal to 5 and scoring equal to negative mean absolute error. Now why this negative mean absolute error? See, why we use mean absolute error, MAE? Why do we use that? To calculate the performance. How? By calculating the error. This is about mean absolute error. That means you are calculating the difference between the predicting data point and the real data point. So you are actually calculating the error. So our aim is that to keep the MAE low. If we keep the MAE low, that means the model is performing better. But see here, we are calculating scoring. So our job will be to make the score higher. Then only we can say that the model is performing better. So we have to keep MAE lower but score higher. Okay. So here what we are doing, instead of calculating mean absolute error, we are making it negative. So if we make it negative, then automatically this will become high. Exactly, we are reversing the process. Okay, because we want to keep it low but we want to keep it high, so we are just taking the negatives. Okay, now as it will give you the negative output, you have to again multiply it -1. Okay, now you can calculate the scores. If you don't calculate it with -1, these values will be negative. Okay, so now the scoring parameter chooses a measure of model quality to report. In this case, we choose negative mean absolute error. And okay, so it is a little surprising that we specify negative MAE. Scikit-learn has a convention where all matrices are defined, so a higher number is better. Right? Score should be higher. Higher means better. So using negative here means allows them to be consistent with that convention, though negative MAE is almost unheard of in elsewhere. Okay, so you understand in scikit-learn they are just following a consistency. Consistency of what? That score will be higher. The higher it is, the better it is. That is in scikit-learn. Okay. Now the problem is mean absolute error should be lower. So that is the reason we are making it negative so that it comes here as higher. Okay. You understand my point? And that's why we are multiplying it -1. Now you are printing the average mean absolute error. So using cross validation yields a much better measure of model quality with the added benefit of cleaning up our code. Okay, now let's do the exercise. For small data sets, cross validation is a great technique because your data points are fixed. So you just cannot separate as training data points and testing data points. So there it is better to use the cross validation techniques. Now let's run this. Pandas, train test split and sell price is the output. Okay. There are numerical columns. Fine. Now let's run this. It will take some time. Okay, so far you have learned how to build pipelines with scikit-learn. It's not done yet. Sorry, this is also not done. Okay. Okay. For instance, pipeline below will use simple imputer to replace missing values in the data before using random regressor to train a random forest model. We set the number of trees in random forest model with n estimated parameter and setting random state ensures reproducibility. See, the same thing. They have created a pipeline. First, they are treating the missing values, then they are passing the model random forest regressor. Okay, so you have also learned how to use pipelines. Exactly. This code below use cross-val score function to calculate the mean absolute error averaged across 5 different folds. Okay, so you have to calculate the error from this one, 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 and then you are making an average of all of them. That is your job. Okay, now let's see. So you have to import cross val score. Now multiply by minus 1 cross val score, pass it through the pipeline. So the steps will be followed, it will be modeled. These are the data points, and you are using 5. You can use any number, and the scoring is negative mean absolute error. Okay, now you can print the scores. You have to run this one also. Sorry. Okay, now step 1. Write a useful function. In this exercise, you will use cross-validation to select parameters for a machine learning model. Begin by writing a function getScore that reports the average over the cross-validation folds MAE of a machine learning pipeline that uses the data in X and Y to create folds. Simple imputer with all the parameters left as default to replace the missing values. Random forest regressor, random state will be 0 to fit a random forest model. Okay, the n estimators parameters applied to get score is used when setting the number of trays in the random forest model. Okay, so they have already passing the n estimator, so you don't have to write like n estimators equals to something. They are passing it whenever they are calling the function. Okay, so your job is to replace this body. Okay, so first you have to do you have to take the xy. So I'll create the pipeline. My underscore pipeline equals to pipeline steps. What are the steps here? First one is preprocessor, right? Preprocessor is simple imputer. Okay, now the second step is model. So model is random forest regressor. Random forest regressor. Okay, here number of estimators that is passed here, so you don't need to declare it here, and random state equals to 0. Okay, now let's run this. Pipeline steps, preprocessor, simple imputer. Sorry, here starting this bracket. Okay, now calculate the scores. Score equals to -1 into cross underscore val underscore score. Here write my pipeline, pass the training data set, and output CV equals to any number you want to give. Scoring equals to, we are going to use negative mean absolute error. Okay, so once this is done, you have to return the value. So return scores, and you have to return the average. Okay, average of all the folds. Okay, so let's say scores. Maybe still okay, sorry, it's written over here, retain the average MAE over 3 CV folds. Okay, that's okay. Now test different parameter values. Now you will use the function key that you defined in step 1 to evaluate the model performance. Okay, so corresponding to 8 different values for the number of trees in the random forest, for 50, for 100, for 150, 300, 350, 400. Okay, so for all of them you have to calculate these scores. Okay, so you just have to run a for loop and store your results in a dictionary. Okay, dictionary is the results, where results I is the average MAE returned by get score I. Okay, fine. So create a dictionary first. Fine. Now you have to create a loop. 50, 50 into 2, 50 into 3. So in this way it is going up to 400. So 50 into 8. So we can create a range of from 1 to 9, right? Now results, and here you have to write 50 into sorry, for I, 50 into I equals to, the function name is get underscore score. So you have to call the function and you have to pass 50 into I. See, for the first time 50 into 1, so 50. So it will be passed to n estimators as 50. So here it will be 50. Okay, so the number of estimator is 50 for the first time. Second iteration 50 into 2, 100. So you are passing 100. So it will be calculated for 100. Third loop 50 into 3, 150. So it will be passed as 150. Number of estimators will be 150. So you have to calculate for 150. Okay, and every time you calculate this, you are storing it in this dictionary. Perfect. Let's run this. So sorry. Okay, now if you want, you can check the output also. Let's see. Print res. Okay. Okay, now let's print the results. See, for 50 this is the score, for 100, for 150, for 200 this is stored in the dictionary. Okay, so use the next cell to visualize your result. See the graph. So matplotlib have been used. Results dot keys are kept in x-axis. So these are plotted in x-axis, that is 50, 100, 150, and these are the values. So values are kept in a list and they are plotted in the y-axis. Okay. So you can easily say that for 50 this is the score, for 100 this is the score, for 150, for 200, for 250. Okay, the score is minimum, you can see from the graph. Okay, now you have to find the best parameter value. So given the result, which value for n estimators seems best for random forest model. Okay, so for that you just can use min function or max function. So let's say I want to see results comma key equal to results dot sorry get. So this will give you for which n estimator you are getting the, just let me print this, n estimators best. From the graph we can see the value 200. Okay, for maximum this is 100. If you write here max, then you can see that this is 100. Okay, so in this exercise, you have explored one method of choosing appropriate parameters in a machine learning model. If you would like to learn more about hyperoptimization, you are encouraged to start with grid search, which is a straightforward method for determining the best combination of parameters for a machine learning model. Thankfully, scikit-learn also contains a built-in function, grid search CV, that can make your grid search code very efficient. That is also kind of similar, grid search. Okay, in any class I will explain what is a grid search. Okay, if you like my videos, please subscribe to this channel. We'll meet in our next class where we will learn about gradient boosting. Okay, so meet in our next video. Till then, bye. Happy learning. Hello everyone. Welcome back to this channel. Let's continue intermediate machine learning. As of now, we have completed up to cross validation. Okay, now we are going to understand about XGBoost. Before this, I will give you a small idea about XGBoost. Okay, whenever you have used any model, maybe linear regression, maybe logistic regression, maybe SVM, maybe decision trees, you have used a single model. But there is a technique called ensemble where you use multiple models together. Okay, it's like taking advice from multiple people so that you can have better idea. That is what is the main crux of ensemble techniques, and it is of many types. You may have heard this term voting, hard voting, soft voting, bagging. Bagging I will discuss. You heard about boosting, stacking, right? We will not go in depth, but we will have just a basic idea about the difference between bagging and boosting techniques. Okay, let's say you have a big data set. Okay, now in case of bagging, what is the method? You are using multiple models. So you have model 1, you have model 2, you have model 3, you have model 4, and all the models are trained parallelly. Okay, remember this term, all are trained parallelly at the same time. Okay, so first you are sampling a dataset from here, maybe dataset 1. Okay, sampled datasets. Same way sample datasets D2 with replacement. Same way dataset D3, dataset D4. You can use as many as you want. I have taken 4. Okay, so once you have trained this model, you have calculated the accuracy, and you have got your output from M1, from M2, from M3, M4. Once you get outputs from all of them, you are calculating your final output. Okay, so you understand the difference between bagging techniques and the traditional algorithms. Here you are using a single model, but here you are using multiple models, and you are creating different samples of dataset. You are training them, and then you are calculating the final output. Okay, this technique is known as bagging, and it is considered that it is better than any particular traditional machine learning algorithms, right? Now, what is boosting then? What is the difference between bagging and boosting? In case of boosting, you have a dataset, and you are taking your first model M1. So you are passing all the features to M1. Now your M1 has predicted something, so it has some errors, or we can say some residuals, the difference between the actual output and the predicted output. Okay, now what you are doing? You have taken your second model M2. So now you have the features and you have the errors. Okay, so you are passing the features plus the residuals, the mistakes done by the first model, so that M2 understand what to do, and M2 is generating output, and obviously some errors. Now you have the same features, so you have features, sorry, and you have the errors from M2, right? And you are passing it to third model M3. Same way, output generated, errors are calculated, again you are sending errors and features to M4. Okay, now see what is the difference between bagging and boosting. Here also you are using 4 models, I'm so sorry, here also you are using 4 models, and here also you are using 4 models, but here all the models have no connection in between, and they are trained parallelly. But in case of boosting, see, all the models are trained one after another, so it is trained sequentially. Okay, okay, so you get my point. Here models are trained parallelly and no model is connected to each other, and here all the models are trained sequentially. Fine. Now boosting is of many types, like gradient boosting, adder boost. Today we are going to read about XGBoost. XGBoost is nothing but gradient boosting, but with some parameters. That's why name is extreme gradient boosting with some extreme parameter. Okay, now let's read this and then do the exercise. The most accurate modeling technique for structured data. Okay, so in this tutorial you will learn how to build and optimize models with gradient boosting. This method dominates many Kaggle competitions, and it is considered one of the best traditional machine learning algorithms. Okay, now for much of this course you have made predictions with the random forest method, which achieves better performance than a single decision tree. Random forest, you know, that collection of decision trees, and which is most of the times better than a single decision tree. Okay, now we refer this forest as ensemble method. By definition, ensemble methods combine the predictions for several methods. In case of random forest, there is several trees. Okay, Now we are going to read about another ensemble method, that is gradient boosting. Now gradient boosting is a method that goes through cycles to iteratively add models into an ensemble. It begins by initializing the ensemble with a single model whose predictions can be pretty naive. Even if the predictions are wildly inaccurate, subsequent additions will address those errors. As I said, that first you are taking the first model, and here you can expect that errors will be high, but slowly after M2, after M3, after M4, this will get improved. That's what they have stated. Then we start the cycle. First we use the current ensemble to generate predictions for each observation in the dataset. Fine. To make a prediction, we add the predictions from all the models in the ensemble method. These predictions are used to calculate a loss function. Let's say mean squared error. There are many loss function. Just think that you are calculating the square difference of actual value and the predicted values. Okay, then you are taking the mean to calculate the error. Now, then we use the loss function to fit a new model that will be added to the ensemble. Specifically, we determine model parameters so that adding this new model will reduce the loss. The gradient in gradient boosting refers to the fact that we will use gradient descent on the loss function to determine the parameters in this new function. I hope you know what is gradient descent. While studying linear regression, you may have seen this, that you have to find where the error is minimum. Okay, so you have to descend. This is known as gradient descent. Finally, we add the new model to ensemble and repeat. See, naive model, the first one, M1, make predictions, calculate loss, you train the new model, add this new model to the ensemble. Okay. Okay. Now we begin by loading the training and validation data. Let's see the code. Same, pandas imported, train test split, Melbourne housing data set we have worked before also. You have all this data, you have to calculate the price, which is the output, and you have created training set, validation set. Fine. Now in this example you will work with XGBoost library. XGBoost stands for extreme gradient boosting, which is an implementation of gradient boosting with several additional focused on performance and speed. Okay. Now in the next code cell, we import the scikit-learn API for XGBoost. XGBoost.xgb regressor. This is the package. Okay. Now this allows us to build and fit a model as we just did in scikit-learn. Same way, you just have to create an object of this particular class. Then you can use fitting. It will train your model. Okay. Now you have to predict the model and you have to evaluate the model. So you are calculating the mean absolute error. Now parameter is the main important thing. That is the main difference between gradient boosting and extreme gradient boosting. That is parameters. Here as we are using many models together, so automatically it was becoming comparatively slow. So to improve that performance and the accuracy, we have adjusted the parameter. It is not a different model. Okay, please remember this. Gradient boosting and extreme gradient boosting, the main difference is in parameter, so that performance and accuracy can be improved. Now the first parameter, number of estimators. This specifies how many times to go through the modeling cycle described above. It is equal to the number of models that we include in the ensemble. Too low a value, underfitting, which leads to inaccurate predictions. You know what is underfitting? That means it is unable to predict in training data and testing data. Nowhere, never. So you never want underfitting. Now, but if you use number of estimators high, then what will happen? Then it will be overfitting. Then it will try to remember all the points. So that is also fine for training data, but not for testing data, right? Because in training data it has seen all the data, so it will predict you uh, almost correct everything. But in case of testing data where it has not seen the data, it will not be able to correctly predict. Okay, so too high a value causes overfitting, that also we know. So you have to keep the values typically between 100 to 1000. Okay, though it depends a lot, and here they have taken 500. So they are training the model. Fine, let's see the output. This is the output. Okay, now the next one is early stopping. Now see, number of estimators, you can fit 500, 1000, 1500. There can be many numbers. So you are using one more parameter, that is known as early stopping that is used to reduce the overfitting. How? After every iteration, it will check whether the score, the performance score, is getting improved or not. If it is not getting improved, then stop the training. That is what is done by early fitting. So, what you can do? You can keep this high, you can use early stopping, and you check after each iteration, and then you can stop it before it reaches the number given by you. Okay, you understand? Let me read this. It offers a way to automatically find the ideal value. So early stopping causes the model to stop iterating when the validation score stops improving. Whenever you see that score is not getting improved anymore, okay, then stop the training. Even if we are not at hard stop or in estimators. Okay, that's what I have stated you. Maybe you have not reached 500. Maybe in 300 it is finding that score is not improving anymore. So early stopping will stop the training. Okay. So it is smart to set a high value for number of estimators. You set it high, but let the early stopping decide whether to continue till the number you have given or to stop before that, so that the model so that it doesn't get overfit. Okay, so then use early stopping rounds to find the optimal time to stop iterating. Now, since random chances sometimes causes a single round where validation scores don't improve, you need to specify a number for how many rounds of straight deterioration to allow before stopping. Sometimes it may happen that after a single round it is not improving. After a single round it is not improving again. So in case of early stopping, we'll stop that. So don't let that do it. Okay, maybe after 3 or 4 times it may again improve. So you just set a parameter. Okay, check 5 times. If it is performing poor for 5 times, then only stop. Okay, it is like giving a chance to a person to appear in his or her exam more than once, so that we can decide whether he is passed or failed. Okay, not in the first exam, but let him appear in the second time, the third time, then decide whether there is a chance of improvement or not. It's like that. Give them 5 times chances. If after 5 rounds also it is not getting improved, then stop it. Okay, or it may happen that it has started improving again. Okay, so that is what they have said. Early stopping rounds. You also need to set aside some data for calculating the validation scores, that you know, that which is done by eval underscore set parameter. This keeps some data aside so that you can calculate the validation score. Now see how to implement this early stopping. Here we have trained this model, so we are just using the parameters. See, XGB regressor, you have created the object, number of estimators 500. Now while fitting, you are passing the training data set. Why training? Now early stopping round is 5. Okay, so tolerate up to 5 rounds, right? If even after 5 rounds it is not improving, stop the modeling. Else, let it train. Okay. Now evaluation set, this X validation data set, Y validation data set, where you will do the validation. Okay, separate data set. Okay. Now verbose equals to false. If you want to feed a model with all of your data, set n estimators to whatever value you found to be optimal when run with early stopping. Okay, learning rate. Now, instead of getting predictions by simply adding up the predictions for each model, we can multiply the predictions from each model by a small number before adding them in. This means each tree we add to ensemble helps us less. So we can set a higher value for number of estimators without overfitting. If we use early stopping, the appropriate number of trees will be determined automatically. So in general, a small learning rate and a large number of estimators will yield more accurate models, right? Though it will also make the model longer to train since it does more iteration through the cycle. This is the default learning rate. Okay. Now, if you want, you can specify. If you don't, it will be default. Now, number of jobs parameter. So, on larger dataset where runtime is a consideration, you can use parallelism to build your models faster. So, it's common to set the number of jobs parameter to the number of cores in your machine. On smaller dataset, you don't need to do this. But in case of larger dataset, you can set the number of jobs, but that depends on which configuration you do have. Okay, so what will happen? You can introduce a little bit of parallelism. So, your model gets trained faster, because that is what is the disadvantage of boosting method, right? You have to wait. After M1 gives you the output, then only you can send it to M2. After M2 gives, then you can send it to M3, right? So you have a problem. That is why boosting is a bit slow in comparison with bagging. That problem is solved by XGBoost, right? By which, by using this number of jobs, so that some amount of parallelism can done. This will make your models faster. See, number of jobs equal to 4, but your machine should have good configuration for this. Now, XGBoost is a leading software library for working with standard tabular data, the type of data you store in pandas data frame, as opposed to more exotic types of data like images and videos. So with careful parameter tuning, you can train highly accurate models. Okay, now let's do the exercise. Okay, so the parameters we have learned: number of estimators, number of jobs, learning rate, and uh, early stopping round. Okay, now let's do the exercise. In this exercise, you will use your new knowledge to train a model with gradient boosting. This is the setup, and you are doing train test split. Okay, so build model. From XGBoost, you have to import XGB regressor. Okay. Now, in this step, you will build and train your first model with gradient boosting. Okay. So, begin by setting my model 1 to an XGBoost model. Use the XGB regressor class and set the random seed to 0. Okay. So, you just have to call this my model 1 calls to this one, and random state equal to 0. Okay. I think you know what is random state. We have discussed many times before. Now you have to feed the model. Okay. So same way, my underscore model underscore 1 dot feed, you have to pass x train and y train. These are the training data set. Sorry. Okay. Now let me run this. Fine. Now set predictions underscore 1 to the model's predictions. You have to predict. Okay. So my underscore model underscore 1 dot predict, you have to predict on validation data. Okay, so let's run this. Fine. Now finally use main absolute error to calculate the MAE corresponding to the predictions for the validation data set. Validation data are stored in y valid. Okay, so mean absolute error function, and you have to pass our output predicted by model, and what is the real output, that is in y valid, right? Okay, now improve the model. Now that you have trained a default model as baseline, now you are going to tinker with the parameters, which is the main thing of the XGBoost regression. So again they are telling you to begin by setting my model 2 using an XGB regressor class, and use what you have learned. Use default parameters, number of estimators, learning rate to get better results. Okay, so you have to train a second model with parameters. So we can write XGB regressor. See, what are the parameters? Number of estimators. So give number of estimators as let's give 500. Okay, now you have to give learning rate. So learning rate equals to, you can give anything, 0.05, by default 0.01. Okay, so anything else, then feed the model. Okay, then feed the model. Dot feed. Same way, you just have to feed the model x train y train. So x train y train. Okay, fine. Next, set predictions to model prediction. Okay, Same way, the model will, sorry, predict x valid. Fine. Okay. Next, use MAE to calculate the mean. What are the things we have done before? We are doing same. Mean, absolute error, and we are passing the predictions done by model and our y valid. Okay, so fine, let's run this. Okay, mean absolute error. Okay, now let's break the model. In this step, you will create a model that performs worse than the original model in step 1. This will help you to develop your intuition for how to set parameters. You might even find that you accidentally get better performance, which is ultimately a nice problem and a valuable experience. You can print this. So if you just run this, let's see. This is the MA, but here let's check this MA. Oh, sorry. See, 18161. Now this is 17101. Okay, so they have stated, okay, they expected that you will perform worse, but you might find that better performance. For us, it's better performance. So it's a nice problem to have and valuable experience. Okay, now they are telling you to set model 3 to an XGB model using XGB regressor. Okay, so let's do it once again. XGB regressor, and you have to set any random set, and they are telling you to change the default parameters, number of estimators, and learning rate to get high MA. Okay, high MA, that's okay, no problem. How can we do this? Change it to 200. Learning rate, change it to 0.08. Let's do the experiments. Feed the model using X train, Y train predictions, all the things. Let's copy now. So this is fit. Here we are going to fit the model. This will be 3. We are going to do the predictions. So right, okay, sorry, to make it 3 you have to make it 3. Now for MAE, here also it will be predictions 3, MAE 3, and sorry, MAE underscore 3. Let's uncomment this and check. Okay, okay, sorry. You must specify the parameters in my model 3 so that it attains higher MAE than model 1. Okay, what should I give so that it performs worse? 17,000, but it is performing better. Okay, let's say what it will provide if I give 100. Let's see, is it performing better or still not? Okay, let's give it 10, then obviously it will perform worse. See, now it is performing so poor. Let's do one thing, change this, give it to 0.1. Now it is improving again. Okay, so you understand, this way you can change these things and give. Okay, number of estimators naturally should be higher because you are training multiple times. Okay, so these things you can do, or you can use these methods also, like early stopping. You can use them also. They have not given in exercise, but try to apply this early stopping round also, right? And play with this. You can use number of jobs also, but depending on your configuration, so you think before you try on this one. And if you want to try, you have good configuration, then you can play with this one. And that time I will suggest you to note down the timing, like first take a time in a particular variable, then after training the model you again calculate the time, subtract them, then calculate how much it is taking. Okay, so you can check how much your speed is improving. If you want, you can play with these things. Okay, so now next thing is data leakage, that we are going to understand in our next class. So meet in our next class. Till then, bye, happy learning. Hello everyone, welcome back to this channel. So let's continue intermediate machine learning. As of now we have completed up to XGBoost. Today we are going to understand data leakage. First we will read, then we will do the exercise. Okay. So before reading out this, let me give you a small introduction about what data leakage is. Let's imagine that your model is performing well on training, or we can say during validation. Okay, so it is giving you a good accuracy, or maybe good precision, maybe good recall value. Okay, whatever metrics you can say, that it is giving you something nice. So you think your model is ready for deployment, so you have deployed your model. But during production, as it is getting some new data points, it is not able to perform. So you might wonder, why is this happening? It is giving you good result during testing or during validation, but not in production, not while doing on any new data points. Why is that so? One reason may be due to data leakage. When you have a data set, you do split, so you make it a training data set and testing data set, right? Now the problem is that maybe your training dataset has some information regarding testing dataset, or your testing dataset have some information regarding training dataset. So what is happening, as both of them know some secret of the other, they are giving you good results. But during new data points, during production, it is getting some new data points which doesn't have this information. Okay, so that is why it is unable to perform. Okay, so you're getting my point. What is happening here? During testing, or we can say during modeling, training dataset has some information regarding testing data points. Maybe it's mean, or some target features, or something, some information which is already known to training, that should not have been known to the training data points, but it is available to training dataset. Same way, maybe testing has some information about the training data points, as both of them know each other, so they are giving good predictions. But in case of new data points, it doesn't have those information, so it is unable to perform. Okay, so this is the reason maybe for the data leakage. Okay, now there may be many reasons for data leakage. Number one, target leakage. What is this? It's like some features which are used for training not available for prediction. Okay, for training you have used that particular features, particular columns, but while doing the training you may not have that access. Let's think that you want to predict whether a customer will default a loan or not. So in your training dataset you have the customer ID, you have the income, you have loan, you want to say missed payment, and whether loan approved or not. Okay, now see, you have this data set. Now here you have missed payment, whether it's false or true. Okay, it may happen. Now think, in this data set, after the person has got the loan, then only either he will miss the payment or he will not. So this column is valid only when the loan is approved. If the loan is not approved, if the loan is not approved, so this column will not exist at all. But if the loan is approved, then only this column may be true or may be false. Okay, so this column is dependent on loan approved column. Now suppose one new data point has arrived. So it has customer ID, income, loan amount, and you want to know whether loan will be approved or not. Now tell me, do you have this column in the new data points, whether it has missed payment or not? No, because the loan is not given yet. So how can we say whether he has missed or not? So this data point is available to training, because this is a old data set. You have collected all the data of all the customer related information. Okay, but in case of testing, you don't have this particular column. Okay, so this is called target leakage. Okay, so these types of problem can arise for data leakage. Fine. Now number 2, while doing data pre-processing, or we can say while doing feature engineering. I'll give you a simple example. Let's think that your training dataset has some missing values. Okay. Now what you are doing, you are taking the your training dataset has missing values. So you have to first impute these missing values. So what you are doing, you are taking the complete dataset and you are calculating the mean value, and you are replacing the nan values with the mean values. Okay, you get my point. You are taking the complete data set, you are calculating the mean value, you are taking that mean value to fulfill the missing values in the training data set. Now what is the problem here? The problem is that you are taking your testing data set from this data set only, right? So you have not split the data set yet, but you have calculated the mean. So whenever you take the test data set from here, the mean is same, almost same, right? So you are getting the mean value of the testing dataset also. So your training dataset knows the mean value of the testing dataset. So you have some information regarding testing dataset. So when you are doing any prediction on this testing dataset, it is giving you a good result, because on the same mean the training dataset is also trained. Training dataset knows the mean. It is modeled, so it has the information. Now while it is performing on testing dataset, the mean is same, so it is giving you a good prediction. Okay, that is a simple example. In this way, many feature engineering techniques, creating new columns or replacing any columns, if you do not split the dataset and you do that thing on the complete dataset, so there may be a chance of data leakage. Okay, I hope you are getting my point. Now another one may happen, data duplication. It's a simple one. It's like the same data points is used for training, the same data points is used for testing. So what will happen? It will obviously perform well, but for new data point it will not be able to perform well. Okay, so that is also a reason. Okay, so these are the this is the basic thing about data leakage. Now we are going to read that and then we will do the exercise. See, in this tutorial you will learn what data leakage is and how to prevent it. If you don't know how to prevent it, leakage will come up frequently and it will ruin your model in dangerous ways. So this is an important concept for practicing data scientist. Okay. Now data leakage happens when your training data contains information about the target. But similar data will not be available when the model is used for prediction. That's what I have said to you. So this leads to high performance on training, but the model will perform poorly in production. We have discussed this. In other words, leakage causes a model to look accurate until you start making decisions with the model, and then the model becomes very inaccurate. Two main types of leakage they have talked about. One is target leakage, another is trend test contamination. Now what is target leakage? Target leakage occurs when your predictors include data that will not be available at the time you make predictions. That's what I have told you. Remember that particular column, whether the customer has missed payments or not, that column is not available to new data points because the customer has not yet received the loan. So you can't see whether that person has missed the column or not. Okay, so that particular column is available to training data points but not to the new data points. So it is important to think about data leakage in terms of timing order or chronological order. The data becomes available, not merely whether a feature helps to make good predictions. So you have to think that whatever the columns you are using for training, whether that particular column will be used for prediction also, whether that column will be available for prediction also. Okay, so just because that is giving you a good, that is helping you to give a good prediction during training, you cannot use that. You have to think that whether that will be available or not. Okay, now an example will be helpful. See, they have given an example. It's like got pneumonia, age, weight, male, took antibiotic medicine. So if you want to predict who will get sick with pneumonia, this is your target column. So the top few rows of your raw data looks like this. Now see, people take antibiotic medicines after getting pneumonia. Once they have got the pneumonia, true, then only they will take the medicine. Okay, so this column is dependent on this column. Okay, so that raw data shows a strong relationship between those columns, but took antibiotic medicine is frequently changed after the got pneumonia is determined. That's what I have told you in that example also. Once you have got the pneumonia. If you don't have the pneumonia, you will not take the medicine. But if you have the pneumonia, then only you will take the medicine. So this column is dependent on this particular column and they are highly correlated. Okay. So this is called as target leakage. You have the target, then only this column is available. Okay. So for new data sets, you cannot expect this column because you are checking whether that person will get pneumonia or not. So you can say whether that person has taken antibiotic medicine or not, because that is dependent. If he gets pneumonia, then only he will take this. So in your target, in your prediction, you don't have that particular column. Okay, this is known as target leakage. So the model would see that anyone who has a value of false for took antibiotic medicine didn't have pneumonia. Model will think that okay, they have not taken the medicine, so they didn't get the pneumonia. They are trying to find the relationship. They have not taken the medicine, so they didn't have the pneumonia. Since validation data comes from the same source as training data, the pattern will repeat itself and the model will have a great validation scores. That's what I have told you, that validation dataset also has the same thing. Coming from the same dataset, you have just separated some data points. So pattern is same, so it will give you a good result. But the model will be very inaccurate when deployed in the real world, because even patients who will get pneumonia won't have received antibiotics yet, and when we need to make predictions about their future health, maybe the persons who has got the pneumonia have not received the antibiotics yet. Okay, so you are predicting about their future health, so this may create a problem. Okay, that chronological may not be set properly, maybe they have not taken the antibiotics yet, right? So to prevent this type of data leakage, any variable updated or created after the target value is realized should be excluded. So you have to find a solution. What is the solution? Just check whether in your data set any column is existing which is only valid after the target column is received. Okay, so I'll check whether this particular column is valid, whether this column is dependent on target column. If it is dependent on the target column in chronological manner, then just remove this from the dataset. Got my point? So you have to simply delete this particular column while training. Okay, because this is dependent on the target column. Now the second, train test contamination. Different type of leak occurs when you are not careful to distinguish training data from validation data. Okay, so what you are doing, you are taking the complete data set, you are doing some data pre-processing, you are doing some feature engineering, you are taking some values from that particular data set, and from the same data set you are taking the validation data set also. So the problem is that validation data set has the information about training data set and the training data set has the information about the validation data set. That's what they have told you. Recall that validation is meant to be a measure of how model is performed. So you can corrupt this process in some ways, which is known as train test contamination. Contamination, the word itself is saying that they are contaminated. Training dataset knows about testing, testing dataset knows about training dataset. Imagine you run pre-processing like fitting an imputer for missing values. So before calling the train test split, okay, so you are not doing the splitting, you are not separating the training dataset and testing dataset, but you are taking the mean value for imputing the column. So what is the end result? Your model may good validation score, giving you a great confidence, but will perform poor during deployment. After all, you incorporated data from validation or test data into how you make predictions. So the may do well that particular data even if you can generalize to new data. Okay. The same thing I have told you, that you are taking the mean value of the complete data set and you are replacing the nan values with that particular mean value. Okay, and that is the mean value of the testing data set also. So what is happening? They know each other and they are performing great. But in case of new data points, the same thing is not happening. They don't have that information, so they are performing poor. Okay, so you have to take care of that also. Okay, now example. You will learn one way to detect and remove target leakage. We will use a dataset about credit card applications and we will check whether a credit card will be given to a person or not. Okay, so let's see. Pipeline created, random forest classifier and cross-val score. Cross-val score we studied in our last class. This is about, let's say you have 1000 data points. Okay, so now what you do, you keep 750 for training, let's think, and 250, sorry, and 250 for testing, and 250 for testing. Okay, so what do? You just divide it into 4 parts. So 250, 250, 250 and 250. Now in your first epoch, you are using this as training, 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 validation. Now you are using training, training, validation, training. Okay, so you are using training. This one is for validation, this one is for training, this one is for training. Okay, so every time you are using 750 for training and 250 for testing, but these 250 are different each time. Okay, So that is known as cross validation score. You are checking it on different data sets, okay, and you are taking the mean value. Same thing. Now the summary is that credit card accepted, reports, age, income, share, expenditure, owner, these are the particular columns, okay. Now you have to decide which column is beneficiary and which is not, okay. So how you can prevent target leakage? So you have to check that whether any particular column is dependent on the target or not, okay. Let's see, they have stated that expenditure column. What is expenditure column? Expenditure column is, you imagine that you have given credit card to a particular person, okay, you are a bank, you have given a credit card to a particular person, and you are now watching his expenditure, okay, where he has purchased how much and when, and you have created your data set. So you have the information about the purchasing behavior of that particular person, okay. Now a second person comes to your bank, and now you are using that particular data set to decide whether you will be given a card to this person or not. But in your previous data set, you have that customer's purchasing pattern. But in case of that new customer, you don't have that particular column. You don't know whether what is his purchasing behavior. Okay. So this column is dependent on, the expenditure column is dependent on whether the person has received the credit card or not. Okay. So it is coming after the credit card is given. Okay. So you have to think whether this column is suitable or not. You can simply remove this column. Okay. So they have checked whether if any person who did not receive a card and had no expenditures, whether a person who has received a card and had no expenditures. Now everyone who did not receive a card had no expenditures, while only 2% of those who received a card had no expenditure. So it is not surprising that our model appeared to have a high accuracy, but this also seems to be a case of target leakage. So when expenditure probably means expenditures on the card they applied for. So since share is partially determined by expenditure, it should be excluded too. Share, see this one, ratio of monthly expenditure to yearly income. So that is also dependent on expenditure. If you think this is a suspicious column, so share also may be a suspicious column, right? So the variables active and major cards are a little less clear, but from the description they sound concerning. In most situations, it is better to be safe than sorry. So you can track down the people who created the data to find more. We would run a model without target leakage. So what you are doing, you are dropping some columns. However, they think that they can be leaky. They have just dropped them, and again they are checking the cross validation score. See, now the accuracy is quite lower. So you think, what we have done, we have made it a poor model, but that is not true. So the conclusion is that maybe if you are considering all the columns right now, you may get a very good result, but it will not perform well in production. But if you are removing those particular leaky columns, so you may now get 80% accuracy, but in prediction also you will get a very good result. Okay, so conclusion is data leakage can be a multi-million-dollar mistake. So careful separation can prevent test contamination. Pipelines can help implement this solution. So do this exercise. Let's do the setup. So step 1, the data science of shoelaces. Okay. So Nike has hired you as a data science consultant. Fine. To help them save money on shoe materials. Okay. Your first assignment is to review model one of their employees built to predict how many shoelaces they will need each month. Okay. They have already built a model. You just have to review the model. How many shoelaces they will need each month. That is your target. Now, what are the features you have? The current month. Okay. Advertising expenditures in the previous month. Okay. Various microeconomic features like the unemployment rate as of the beginning of the current month. Okay. And the amount of leather they ended up using the current month. I think in this way that whenever I get any new data points, whether this will be available. So current month will be available. Fine. Advertising expenditure in previous month is available. I am calculating for January, so I have the data for December. Fine. Various other features like the unemployment rate as of the beginning of the current month, that is also available to me. Okay, so I'm predicting for January, and for beginning of January I do have the amount of leather they ended up using the current month, that is not available to me. So that is I think for me it's maybe a problematic. Okay, let's see what they are saying. So this is tricky and it depends on how data is collected. Would you at the beginning of the month, then it is fine. How much leather will be used? If so, this is okay. Exactly. But if that is determined during the month, you would not have that access. If you have a guess at the beginning of the month and it is subsequently changed during the month, then the actual amount used during the month cannot be used as a feature because it causes leakage. Okay. So For beginning you can take, but for the end of the month, no, that is a problem. And here, second one, you have new idea. You could use the amount of leather Nike ordered rather than the amount they actually used. That is a solution leading up to a given month as a predictor in your shoeless model. So does this change your answer about whether there is a leakage problem? What do you think? Okay, so you are not using the amount they have used, but you are using the amount they have ordered and as a predictor in your shoeless model. So I think this can be fine. Okay, because you are getting this as much Nike has ordered. Let's run this. Let's check what they are saying. So it could be fine, but it depends on whether they order shoelaces first or leather first. If they order shoelaces first, you won't know how much they have ordered when you predict their shoelace needs. If they order leather first, then you will have the number available when you place your shoelace order and you should be okay. You go through these things, okay, and think. Getting rich with cryptocurrency, okay? So you have saved Nike so much money but that they have given you a bonus. Fine. Your friend, who is also a data scientist, says he has built a model that will let you turn your bonus into dollars. Specifically, his model predicts the price of a new currency, Bitcoin, one day ahead of the moment of prediction. Okay, so his plan is to purchase the cryptocurrency whenever the model says that it is going to go up. Okay, whenever your model will say the price will increase, so you will buy some cryptocurrency and that will make you millionaires. Okay, fine. What are the features? Current price of the currency. Okay, fine, available to you, no problem. Amount of the currency sold in last 24 hours. That is also fine. Change in the currency price in the last 24 hours. That is also available for new data points. Right? Change in the currency price in last 1 hour. That is easily available. Number of new tweets in the last 24 hours that mention about the currency. That is also available to you. Okay. So the value of the cryptocurrency in dollar has fluctuated up and down by over $100 in the last year. Yet his model's average error is less than $1. So he says that is proof his model is accurate and you should invest with him. Buying the currency whenever the model says it is about to go up, is he right, and is there any problem and what is it? See, these data are all fine, that we can see these are all available. Now the value of cryptocurrency in dollar has fluctuated up and down by over $100. The cryptocurrency is actually fluctuating. Okay. Okay, so his model's error is less. So this is fluctuating, but his model is performing well. And he says this is the proof that his model is accurate. So let's see what they are saying. Okay, so no source of leakage. That is fine because we have all these columns easily available. Those features should be available at the moment you want to make a prediction. Exactly. So they are unlikely to be changed in training data after it is determined. But the way he describes accuracy could be misleading. Okay, why? If the price moves gradually, today's price will be an accurate predictor of tomorrow's price. But it may not tell you whether it's a good time to invest. Exactly. For instance, it is 100 today. So a model predicting price of 100 tomorrow may seem accurate even if can't tell you whether the price is going up or down from the current price. A better prediction target would be the change in price over the next day. If you can consistently predict whether the price is going up or down, you may have a winning investment. Saying that this can tell you the model predicting in change of price, but it is unable to say whether it will go up or down. Okay. So, step 4, preventing infections. An agency that provides healthcare wants to predict which patients from a rare surgery are at a risk of infection. Okay, so which patients may grow an infection after a rare surgery. Fine. So, it can alert the nurses. Okay, so you want to build a model. Each row will be a single patient. Okay, about every patient who have received the surgery, and the prediction target is whether they got an infection or not. Okay, some surgeons may do the procedure in a manner that raises or lower the risk of infection. But how can you best incorporate the surgeon information into the model? Some surgeons may do so that the risk gets lower. Okay, so okay, you have a clever idea. Take all surgeries by each surgeon and calculate the infection rate among those surgeons. Okay, so for each patient in the data, find out who the surgeon was and plug in that surgeon's average infection rate as a feature. So do you think there is any target leakage? See, first of all, you are taking all the surgeries by each surgeon and calculating the infection rate. Second, you are taking each patient data and finding out who was the surgeon and what was that surgeon's average infection rate as a feature. So, see, there is a problem of target leakage. See, if we calculate the surgeon's infection rate using all their patients and also for which we are going to predict, then we are using a future information to make a prediction, right? We are using a future information because we are taking all the infection rate of all that that particular surgeon's patient. So that is kind of cheating, right? What we can do, we can calculate that surgeon's infection rate using only the past patients, right? Not that new patient for which we are going to predict, right? And see, there is a trend test contamination also. How? If we are calculating the surgeon's infection rate using all their surgeries, that is in the test set also, the model learns from the test data. So it is actually looking better, but in reality, the model will not have that future data. So new patients' predictions may not be correct, right? Because we are taking all the infection rate from all their surgeries. So test set also has those data. So they know the information, but from the new data point, we will not get that information. Let's see what they have stated. That will help us to understand better. Exactly. So if you have target leakage, if a given patient's outcome contributes to the infection rate for the surgeon, which is when plugged back into the prediction model for whether the patient becomes infected, you can avoid the target leakage if you calculate the surgeon's infection rate by using only the surgeries before the patient we are predicting for. Exactly. For the past patients, right? And you also have this problem because including those from the test set, the result would be that your model could look very accurate on the test set but not well when new data. Exactly. You just read it, go through. If you don't understand, you can write a comment. Okay. So step 5, housing prices. You will build a model to predict housing prices. The model will be deployed on an ongoing basis to predict the price of a new house when a description is added. Okay. Now, how do you think? You will always think in the same way, that take the new data points, okay, and think that whether it has all these points, all these features. If yes, then there is no leakage. See, size of the house, yeah, that is available, that is no problem, because once your house is created, it will not change. So you have this, fine. Second one, average sell price of homes in the same neighborhood. Think how average sell price is calculated. You have to sum all the prices of the homes and then you can calculate the sell price. So it is not something which is fixed, because it is going to be changed, it is going to be updated whenever you are you are selling any homes in that neighborhood. This will change. Okay, so after every selling, this is going to be changed. So this is something which is dependent on future also, so that is a problem. Okay, there should be no columns which will be dependent on future. Latitude and longitude, that is perfect, that never going to be changed. Whether the house has a basement, that is also fine. This is like size of the house. Okay, but average sale price of the homes in same neighborhood can be a problematic. Okay. Now, conclusion, leakage is hard. You should be proud if you picked up on those issues. Now you have the tools to make highly accurate models, pick up on the most difficult problem. There is still a lot of room to build and experience. See, there are so many things regarding leakage, and want me to make one detailed video regarding data leakage, then please let me know in the comment sections. I'll do that. Okay. So now I'll give you a homework. Tell me what are the things you can do to prevent this data leakage. Okay. So you are requested to kindly comment writing how to prevent. What are the steps you think you can follow to prevent data leakage? So this course is completed, intermediate machine learning in Kaggle. So meet in our next class. Till then, bye. Happy learning.